I'm going to do a quick overview of the state of the power pallet, past, present, future. The point of this is to clarify where this has been, where it is right now, and what you can imagine coming in the future. So we're going to go through, probably most oddly, stuff that doesn't exist right now, stuff that we think is weak right now, stuff that we think can be improved on the core unit, as well as things that are going to be add-ons. So we tell you all this because most everyone wants to work with this is in this kind of as a longer arc development and deployment project. So if people are looking to do things with multiple units out in the field, it's important that they see our general product development pathway to know what they'd be working with down the road. Okay? What exists right now has no intrinsic, it's not a given what exists right now. This is where we are in the development process, and we are constantly improving these things and trying to do it in a manner that every time we improve something, it's something that can be retrofit back onto the machine. That sometimes works, sometimes doesn't. But it's important that we are working to a puck that is going way down there. The puck is here right now. The current state of things, we're very happy for pilot stage projects, individual projects, people that are looking at doing hundreds of these units. There's new things we want on these things for those projects, so that's the types of things we're going to be going through in this. This process, or this project, started building gasifiers as experimenters kits. As most of you know, the GEC, the motivation was to try to give people a Lego system, to try various reactor configurations, various ideas that we were all debating on the online lists, but didn't really have any materials to build it. So we tried to create this platform that we could actually do some comparative testing between different sites. We'd bring up the conversation and have a little less superstitious thinking about actually what makes these things work. That went wonderfully. It was a very simple unit. We made probably 300 of them. We're still making them. They are in about 60 different universities at this point. They have become a common research tool that's used around the world. Okay. We came up with a very simple building method to do that was based on that CNC plasma cutter in the back room and sheet metal. Well, it was sheet metal and black pipe plumbing. The building system was limited to, we could only use sheet metal or black pipe plumbing or something that you could get commonly in hardware stores. And in fact, in the beginning of it, I walked every row of Home Depot here trying to get into my head, what is the toolbox if I'm going to limit myself to readily available retail hardware? What do I have to build a gasifier? Okay? So we needed something that was going to require some exotic custom part. We had to redesign whatever the assembly was that got us into that dependency. So that was all fun for DIY play, and got a huge installed base around the world. We actually got people involved in the process of learning the science and engineering. Went through a tremendous amount of different building methods. We did product testing and market research or refinement by actually having low-cost machines out in the world. It's very much like the early PCs that were soldered together units. They went to enthusiasts. No one was really sure what they were going to do with it, but there was this great promise in the concept of it, and people wanted to start playing with it. Okay. So we very consciously did that same route on the gasifier. Okay, and as you know, we had all the files online, so people wanted to go build it. They could download the files, either cut it out manually or take it to a local CNC or laser shop and get it cut, and then they weld it together. Okay. Now, as we went along, the problem we found was that very few people were actually getting those kits to anything resembling a real running gasification-based power system. They would get them up and play with them as a demo or a show, but the amount of expertise that they had to acquire to really run those well and finish out all the details of the system was overwhelming most users on the other end. So we went progressively in this direction of, well, what we really need to deliver is a power generation system, not a gasifier. and that once we're delivering the power generation system, the needs in that, the drivers in that, are the end value of it generating power at the easiest amount possible, and less so a lot of the flexibility of the core gasifier. Okay? So one of the core things that's going on with us right now is, while the GEC and the early power pallets have been the development platform for refining this product, we still have a lot of the design and making methods on it that are optimized for modularity, flexibility, lots of points to stick instrumentation in, lots of flanges to take things apart, put different things on. It's still, the raw gasifier itself still has some of the characters of the Lego kit. Now, Legos are great, but you never use Legos to build your final building. It's a modeling environment. So when you start looking at something to get to very long run times and resistant to operator error, like all of those flanges and ports and whatnot, those are air leak points. Those are potentials for error. Those are potentials for people to change things around and make problems. Okay, so where we started wanting fingers in this thing all over the place, the further we've gone along, the human fingers have become more of a problem, which makes me very sad. But we're trying to design the human out of the system right now. Okay, so anyway, so we've been developing the power pallet platform, as you know. The point here on this is to say, well, what we want a complete system from beginning to end, not components, not build up on the other end. That really what's meaningful is not to deliver the engine of the car. Maybe someone else has a transmission, but you deliver the entire car fully integrated, all the parts together, so you can get in and drive it. Okay, so that's the goal of the power pallet, is a complete biomass power generation solution that converts woody biomass into electricity, heat, shaft power, and some other things we'll talk about later, and trying to do that at a full system price in the $1 to $2 a watt. Okay, my own personal kind of grail in this is I think these systems should cost $1 a watt. If you can get the total system beginning into $1 a watt, the economics are so obvious that it'll go viral. Okay, and we're close to that, but also with things like the hoppers not being how we want them, and user issues still needing refinement and what have you. Okay, so over time we went from the 10 kW to the 20 kW. In the beginning, I thought that the main point of this was going to be very small units and people really working at micro scales by a house, almost like a CHP unit, natural gas CHP unit you put on your house in Europe. And we found really that the greater demand has been for the 20 kW units, and even higher than that, where the main use that people are wanting to put these things into is primary power in a business application or in a agro-industrial type infrastructure situation. They want more than 10 kW. 10 I thought was the minimum to do because you can run a welder reasonably on 10. You can start up well pumps and whatnot. But if you want to start running a much larger factory, you run out fairly quickly. So the 20 is taken over the orders, which is also good for us because it doesn't cost us that much different to make them. So we basically make no money on the 10. The only thing we make money on is the 20. Okay, so the 20 is kind of, just by choice of people buying, the 20 has become the main thing that we're selling. Okay, and will become even more the focus as we go forward. Okay, we went through a little bit earlier of us building out our manufacturing strategy here. And the main feature of that is not doing it here, but rather making all of our suppliers our manufacturing facility, and this being a last stage assembly. Okay, and this was a lineup a few months ago when we were doing something. Okay, so 5 years after we started, well, the first one went to a professor in Canada who called me, and I'd been doing all this stuff online, and he begged me to make him an experimenter's kit. And then I got the notion of doing this unit that you could change out between updraft, downdraft, crossdraft, different heat recycling things. And that led to the GEC. We went through all the process of the GEC, and at the end of 5 years, we have about somewhere in the range of 500 systems out in the world between the GECs and the power pallets. They're in at least 40 countries. I think that's larger, and in over 50 universities. Okay, we're starting to see PhD theses come out that are based on these. We're seeing some collaboration between sites. We could certainly get much more of that, but it has created a very interesting shared platform for this work. And certainly, as most of you know, it's really resurfaced this conversation. I mean, there was no, other than the gasification list, there was no like online building environment for these things. And now we have multiple ones, multiple people making kits. And there's about 7 different kit makers at this point that have been done largely on this web-based model. Okay. And the map of where things are, it looks something like this. You see this great density in the southeast of the U.S., or actually all over the U.S. Surprisingly, these are all the early kits. There's less power pallets in this area. Really, the things that are driving it currently are all international. We export, our sales are probably 70%, 80% international at this point. So we manufacture on the most expensive real estate and labor market in the world, and then we export it. Okay. Is it 80% right now, you think, Dusty? He says at least. Okay. So really the drivers of this are overseas right now. It's much less locally. When it was a DIY hacking device that was much more interested in the U.S., once it became an energy proposition, it's much less interest in the U.S. Okay. So, and like we said, we're interested in finding major centers, not just you have a nice logo. Some of these are pulled up mostly because they're nice logos, but places that people are really doing consequential work and being sites to leverage this out of. Okay. You also notice some very interesting holes on the map where the conditions are fabulous for this, and there's nothing there. Okay. So, why are we doing this other than the obvious point of providing electricity? The larger idea of what I was captured by here was the ability for a thermochemical-based device to create kind of a new type of a personal scale power appliance. I was interested in something that you could get small enough and expert enough that you could take it to where the fuel byproducts were, or the organic byproducts were, and convert them locally into multiple types of power products right where they're needed. Okay? In the U.S., most of the energy discussion, or if we're going to have alternative energy installed, we're going to say, well, we're going to get some solar panels. Well, that's nice, but that's one of many different energy types and even product types that we use fossil fuels for. Okay? So just on the energy side, any house or business has electricity needs. They have heating needs, usually cooling needs. In the developing world, there'll be shaft power needs. Of those four, you get one out of PV. The collection is too broad to do any meaningful heating out of it, but you can out of CHP. Not CHP, CSP, concentrating solar. Yeah. So we were interested in how much can we use the conversion pathway of gasification to create this block where we can have multiple types of power coming out of it and be able to vary those things in relation to what the needs are on the site. So sometimes there's a need for more heat, sometimes electricity, sometimes cooling. Okay. And then as we went on and we started to find that there was these other product types that were particularly or possible once you had an engine, and because you were working with a solid input, not sunlight, you could also make interesting things like biochar. Okay, we'll get to a whole variety of those. So we saw there was also these other product types that can come out of this that are as equally interesting as the power types. Okay, so that kind of led to the notion of what we were doing here is we were trying to create a tool. It wasn't just a service that electricity shows up at your house, but this is a flexible tool that you put in someone's possession, and they can have determination and enablement across a whole bunch of power and product problems. Okay, and then they can vary that and to deliver it as they need locally. So the metaphors were you're trying to create a PC of energy or a washing machine of power. Something is a new type of energy appliance that you put in a house or a business that deals with its waste, takes bad things in, and has multiple types of good things coming out. Okay? That we call the magic box. So what we're trying to get to in all this is the magic box that takes in bad things, and many different types of good things come out. Okay? Now you see variety of biomass here goes into this converter. Right now, most all we're working with is electricity. Okay? But the long arc goal and big idea that we're working towards in various product development pathways is to cover all of these power types and all of these product types. Okay? We started with electricity because, well, electricity is the most obvious economic case. Okay? It's also the easiest. Once you have the engine turning, you put a gen head on it and you get electricity. Okay? Well, maybe shaft power is easier. In the beginning, we did have shaft power, but with the Kubota engines, but the access to the front crank got complicated with a different radiator kit, and we're going to be getting back to that soon on these. Okay, the heating portion here, we've been basing all these on water-cooled engines, such that we can add a heat exchanger to the water, as well as a heat exchanger on the exhaust, and now have a loop for a working fluid to take the heat off. This heating or CHP project is happening with a project we're working on with Biodeco out in the Central Valley that is a multiple types of conversion of agricultural waste. So I don't have any pictures of this up here. We've built out a prototype, and we hope to, in the beginning of the coming year, this becomes a regularly available option. Okay.
That's just an addition to the generator.
It's some extra components, plumbing, as well as control to keep temperatures correct and not have explosions.
So it's still generating electricity?
Yes, it's using the waste heat. Remember, an engine is primarily a heater with a small byproduct of mechanical energy. Okay, so you're using, so you have a lot of heat to work with. And there's one thing which makes working with engines very, very interesting, is to the degree that you want to touch all these multiple product types by starting with a heat-based engine, and you try to get your efficiency up as high as you can on the mechanical to electrical portion, and you're going to top out in the 30% sort of range. You have all this heat to deal with. Okay, you can do good things with that, and that can be a feature, not a problem. So most of the places where these things are going, whether it's developing world agricultural processing, or it's going to Italy on a small farm, there's heating needs in these places. That's usually a critical part of the output and and it's a big economic driver of what makes the total economic proposition work. Okay. The cooling part of it, once you have heat, there's lots of opportunities for adsorption or absorption chillers. They're very expensive, but there's some interesting new things going on there that we think we can get one of those into a reasonable cost add-on. Okay? The amount of waste heat coming out of the system is such that an absorption chiller, if you were to plug all the power, electric power of this into a refrigerator, or use it for a refrigerator and air conditioning, the amount in cooling you would get is to an approximation about the same you would get as using the thermal route. Okay? So you can set up a situation where you can equal what you're going to get your refrigeration out of electricity, use the thermal part, and now still have the electricity to do something else. Okay? Haven't started on that one yet. We're looking for projects on that. Okay? On the product side, the biochar was always the one we wanted to start with. Which the biochar is. Does anyone in this room not know what biochar is? Okay. So biochar is the intentional introduction of charcoal into soils. It has all sorts of beneficial impacts on plant productivity and soil health. You get significant increases in growth, retention of minerals, mineral density in the plants, and curiously, to the degree that you put the charcoal underground, it's very stable, so you're removing carbon out of the carbon cycle. If you leave plants as biomass, they rot very quickly because the volatiles in them, animals start eating them. Once you turn it into charcoal, it's very stable. So the interesting thing in working with a thermochemical process off of biomass, the biomass itself just was gas in the atmosphere. If you burn it, it goes back to the atmosphere, you can claim a carbon negative cycle over a longer time period. If you take part of that biomass and convert it into biochar and put it in the ground, you're combining a power generation scenario with an agricultural scenario, and that total power generation cycle is carbon negative. It seems impossible. Okay? You're taking a waste, which is a problem. It's typically free. You're getting a energy value out of it, which has a market. You're putting a byproduct into the soil, which is improving your performance in agriculture, and that at the end of doing all of that, you have less carbon in the atmosphere than you did when you started. Okay? So the amazing win-win-win in the end of these things is a waste to energy and agricultural provider that's a total carbon negative cycle, so that the more you run it, the more you improve the greenhouse gas situation on the planet.
How detrimental is heating up the biochar to the level that it's heated in the power pallet to the qualities of biochar in the ground?
Well, if you just say, well, the charcoal coming out the end is biochar, it's gone all the way through the hearth and it's been fully devolatilized. It's not ideal biochar. But we'll go through here in a second about what we're doing. There's a pre-hearth takeoff that we're working on. So when we say it's an integrated energy biochar, it isn't just we're taking the junk out the end and saying, oh, by the way, this is biochar. There's a dedicated system that makes it. Okay? So biochar, huge addition here, and we're working on this currently. Clean water. I've been surprised how much demand there is for clean water across the exact same map that there's energy challenges. Okay? So once you have heat here, if you have a source of dirty water or water that needs to be purified, you can run it through flash distillation cycles and clean it up. You still need the water to start with, but you can use it as a purification system. So we're imagining in time here that we will be integrating water purifications, heat-based water purification systems into this platform. Okay? Alternative cement. Ariel, who's one of the majors here, runs manufacturing. He grew up at the Center for Maximum Building Potential Systems in Austin, Texas, if anyone knows that. They do a lot of alternative building materials for the developing world and do a lot of alternative cement work. So, cement is very energy intensive, requires potable water basically to make it. And there's some very interesting mineral complexes that are commonly found in your charcoal coming out of these things that have promise to be the foundation for alternative cements. Okay? We haven't done any specifically on that yet, but their work has been putting together mineral cocktails that are very closely related to what we're just seeing coming out of this. So we think that there's some building materials there in the end. Okay? And of course, gas to liquids. And this is, of course, the grail, the thing everyone wants to do with this. It's also the most hard problem. But in time, once you have the CO and H2, there's all sorts of pathways that you can up-migrate that to various liquids. So gasoline, diesel, alcohols, other chemical feedstocks. They're all very difficult, but at some point here, one of us is going to figure out how to make it simple. Okay? But I'm still waiting. Okay?
CO2 to your products.
What?
You need to add CO2 to your list of products. Carbon dioxide.
Yeah, that's true. You're right.
You're going to hear more and more about it.
Okay. Okay, so we keep finding other little ones here, but this is the big idea. We're not making a generator. We're making a multi-gen, an octagen, agnostic converter of byproduct waste into multiple types of power and product out that can be varied depending on your use at your site and throughout the year or throughout the day as you want to do one thing or another, and try to hit as many of these different things that we currently use fossil fuels for. Fossil fuels isn't just an energy, it's not just the input to energy. It's the input to the petrochemical process. It is why we have agriculture. We do all sorts of things with fossil fuels. So the fun thing with biomass is you have the same atoms. You have the same hydrogen, carbon, and oxygen atoms. You, in principle, can make all of those same products that you're making out of fossil fuels. So, all over this building and on papers that you're not seeing are various product development pathways that pick away at this larger magic box. Okay? This skid that you're seeing right here, as of 2 years ago, was premised and organized, and all the components are on it such that an enclosure goes around it, and a very different hopper assembly goes on it. And you've probably seen that around here. This is the sort of thing that we're going to. It's a fully enclosed skid with what we call the rooftop hopper, which is a very wide, not tall hopper that will take significantly larger amounts of fuel than this. It's challenging because you can no longer have a taper, so we have a variety of different scenarios for doing some scroll bars that pull that into the center to feed actually into the reactor. There is generations and generations of work going on to lower all of these other components, most significantly the gasifier. And that feeds into like how are we dealing with the ash system on the bottom? You know, why don't we have a continuous ash out? Well, we could put a taper on there down the bottom of the reactor, put an auger in and come off, but we would add about 8 inches to the height of the whole thing. So we're picking away the height on this bit by bit, trying to get to a solution that is about to this high when you walk up to it, to the top of the hopper. Okay? And the details of our product development pathway are dealing with all of the different fronts that walk us towards that. Okay? So, other things on the power pellet evolution front. I'm going to go through some things that we've done already and some other things that are coming. Okay? On the units that we've been delivering recently, we've redone the flare mount and rerouted the gas and remounted the blowers. As we were referring to earlier, we're having a lot of problems with people destroying the blowers. So we changed that whole architecture around such that the blowers are self-emptying, and then the gas itself is going through the filter on startup such that you can't get the blowers in trouble if you do something wrong on the early startups. Okay? So that's been going out in the world for a long time. If you have an older power pellet, we have a retrofit kit that reroutes the gas through the filter, so you can change it to most of what we're doing currently. We've done a lot of work on the gasketing and plumbing sealing, trying to prevent air leaks through all of these flanges and bungs and whatnot. Particularly when people take these things apart on the other and put them back together, you get air leaks. If you get air leaks in the wrong place, things burn out inside. You have hot gas inside these things to the degree to which you get a leak at where the gas is of reasonable temperature, it lights on fire, you burn your gas, and you also burn out things inside. Okay? So we've been doing a lot of work on the gaskets and sealing. As you know, we've been delivering grid tie equipment and paralleling equipment. We can make it work. We're seeing it's a little less plug and play than we'd like it, given the realities of what you have to configure to on the other end. It's not just connecting the wires. There are PID loops and thresholds and whatnot that need to be moved around, both in the grid equipment as well as our governor, to get it to sync and stay and have nice failure states. So right now it's taking on-site work to work out all of those particulars. In time, we're going to probably reduce it down to things that are fairly well known and not have to do it on site. But right now, the grid tie installations, we have to go and do them. Okay? The grid tie systems have also allowed us to start paralleling, as we went through before. So we can put multiple units together, take multiple units into the grid, or put multiple units together and go to an off-grid situation. Those have, again, different configurations. Some of the equipment to do it moves around, but getting over the basic hump of being able to sync between 2 units or a unit in the grid, as well as control power moving, you start to have all of these other architectural flexibilities. Okay, so that's been a huge win, and it's opening up all sorts of project situations that we couldn't do before. Okay, and to do it at a relatively low money add onto the system. Okay, improved electronic control and diagnosis. We've been doing. There's constant software updates that are coming out of this. We've been able to add a smart auger system that senses when there's binding, and it takes it through recovery runs to try to move the stuff out of the way through repeated forward and reverse action. We're slowly over time trying to build something that's like an onboard diagnostic system like you see in a car. such that you're doing more than just regulating the system, but you're also diagnosing what things have gone wrong. And you do that by having full maps of the entire system, and you can see when things go out of out of range in relation to the other variables and processes. You can also diagnose, has a motor failed or whatnot. All of these things have signatures through your instrumentation. So we're progressively building up a system that will have that type of expert onboard diagnosis, and once you get to a remote monitoring, you can see all that stuff from a distance. Okay? So, and that's very important in the larger project of trying to eliminate the operator expertise that's usually the hurdle to get these things deployable on the other end. Okay? Some stuff that we're working on right now, as you've probably seen around the building. There's a larger hopper project going on that's about twice the size of this, sitting on the table out there. That's going to go into the queue fairly soon. We're doing a new mixer architecture that's mounted on the filter, no longer off on the engine. Again, remember we're trying to separate the different components on here. That mixer in time will have a feed-forward control, such that right now when you have a big step load on the generator, that change in gas flow, there's a differential in the rate of change on the air side versus the gas side, such you'll go out of mixture until your oxygen sensor says you're out of mixture and correct. Well, you can predict all that stuff and build it into the software so it auto-corrects before you read it. So right now the mixture system is fully reactive. It's going to go to proactive once we get through this new mixer. Okay? And those are minor issues. I mean, you see it tracks, you turn things on and off, it tracks, but there's improvements we can do there. Continuous ash out. Again, these units are premised on a batch mode operation. You can run this about 12 hours before the ash fills up. We're developing continuous ash out systems that partake of a scroll in the base of the reactor, so we don't need a taper. The scroll brings the ash out to the side, and then we can take the ash out and take it wherever we want. Okay? So that's going on. We're all annoyed that the cyclone is in the middle of the thing, and the bucket's under there. I was put there because that's where we want the heat. We want the heat there. Who cares about the humans? We want the heat there, and it should go straight into the drying bucket. So that's why the cyclone and drying bucket are lined up. But that bucket there is annoying. So there's evolutionary changes going on that are moving the cyclone out to here. Okay, so it sits right on the side. So then all of your byproduct removal things are here on this side of the power pallet. Okay, so it's one side emptying. Okay, so that's some of the things that we're working on in steps across the power pallet. There's also just completely new components. There aren't kind of fixes or refinements of usability, but totally new things we're doing. And you've probably seen these around the building. Again, there's a full CHP process going on, which I sadly don't have pictures of it here. The actual unit's out in Fresno. But we're trying to get to a mature CHP system that is in situ on this within the frame of the skid, not something that's added on the other end with hoses and new mountings and whatnot. So we want to be able to, in the beginning of next year, deliver a CHP add-on to this that can be delivered integral with in, out, run your working fluid through here. Okay, turbo. As you've probably seen out in the back, there's one of the 20 kW power pallets that we're working on a turbo system for. And we were getting up to 25 kW. We're very happy. Remember, the gas that's coming out of a gasifier, it's a very energy-unrich gas. However, it has some other characteristics that make it interesting to hot rod. It's a very detonation-resistant gas. It's kind of like, in some ways, it's like setting an engine up to run on methanol. It'll take in the 17 to 18 to 1 compression ratio. It's the usual claim. We don't know with the turbo how far we're going to be able to push it, but in principle, starting with these engines, which are about 10 to 1, we should be able to get close to doubling the dynamic displacement of the engine. Okay? And because you've so derated the engine with this energy undense fuel, putting a turbo on it is just bringing it kind of back up into its mechanical design area. So to get to this form factor, we're using inline engines. We're choosing ones, or things are arranged such the exhaust is coming out towards the gasifier, such we can get all the recirculation. But this is the biggest 4-cylinder engine we can find at reasonable price point. This is a 3-liter 4-cylinder engine. I would love to have a 5-liter inline 4. Can't find it. So we can do some increase in displacement dynamically with forced injection or induction. Okay, so the goal is, again, by sometime early next year, to be able to deliver this 25 kW turbo system as a regular product. The only ones we're doing right now are into Italy, and that's the first destination and refinement site for these. But in time, they'll become a regular product that we're doing. Okay? Biochar takeoff. So some of you have noticed that this pyrocoil here, being driven by the external heat from the engine, is somewhat like a pyrolysis retort. We have a heat exchanger. We're bringing in dry fuel, and then through the jacket, taking heat into that bed and making charcoal. Okay? We're not relying on all the hearth issues down here, or the heat from the hearth. And actually, by the time the charcoal gets, or the material gets down to the hearth, it's fully pyrolyzed. So the long intent has been to take a biochar takeoff at the end of this pyrocoil. A takeoff that is taking charcoal that has been heated through a wall with gas about 600 C on one side. The charcoal gets up into the 400 and 500 range on the inside, which is exactly what we want for biochar. Okay? So we're coming up with an elaboration that has a char takeoff here pre-hearth. Okay? So out back, if you look at some of those reactors that are built out there, you can see at the base of the reactor and a hole through the side through which an auger will come and be able to pull this out at variable rates. When we were working on the BEC, it wasn't really announced, but a lot of what I was doing in the BEC was trying to understand a vertical retort that was sized exactly as the size of that pyrocoil. Okay, the BEC is that pyrocoil made a little taller and with all of this other process control stuff around it, such that we could study a vertical retort. Okay, with the notion that in time, that time has unfortunately turned into 2 years, that we collapse these into one thing, that the BEC, all the functions of the BEC are integrated into that pyrocoil that's on the standard GEC toddy. Okay? So the outcome that we're trying to get here is the ability to select biochar out of it to an amount you want versus the amount of energy you want, and have that come out pre-hearth such that you aren't getting high temperature biochar that's been fully devolatilized. So gasifier evolution. We're also doing a lot of stuff on gasifier evolutions, moving this from the architecture, the building architecture that was based on the modular kit, to something that is not user accessible, something that is less flanges, less bolts, less throughputs, less potential places for error, and an ultimate higher longevity. So if you look out back, you'll see a whole variety of reactors that look vaguely like this. It's all mostly the same parts, but redone in their building method. Okay. So some things that are going on in that is we've combined the reactor assembly and the pyrocoil assembly into one thing. The most impactful add on this is most likely the pyrocoil. And we originally had that as an add-on to the basic reactor, but for what we're doing with these now, that you never don't want the pyrocoil. That's the point of the thing. And when you look at how it's built, it ends up kind of suggesting that it should just be part of the reactor. So we've gone to a solution that the reactor is now built with this double wall solution of the pyrocoil, and we have one piece there instead of the two pieces. Okay? The old way this was built here, here's our reactor. The pyrocoil bolts down in, the drying bucket to the side. We're going now to a solution where here's the new reactor. The reactor and the pyrocoil are a single unit that slide down inside here, and the double wall jackets are integrated within the reactor. Okay, so let's go get some food. So we're going to go eat across the street again, and afterwards we're going to come back here and do some more things.